Hello, everyone. My name is Ziwei Mao. I'm a master student in computer engineering. Today, I will be giving you guys the presentation of AutoSys, the design and operation of learning augmented systems. Before we start, I'd like to introduce you to two concepts if somebody is not familiar with it. The first is machine learning. Machine learning is algorithms that can parse data, learn from that data, and apply what they've learned to make informed decisions. Machine learning fills all kinds of automated tasks. It's something that performs a function with the data given to it and gets progressively better over time. The second concept is deep learning. What is the difference between deep learning and machine learning? Deep learning is a subset of machine learning. Deep learning is considered an evolution of machine learning, uses a programmable neural network that enables machine to make accurate decisions without help from human, where machine learning do. Let's get to the paper step. AutoSys. So what is AutoSys? AutoSys is a framework that unifies the development process of several learning augmented systems at Microsoft. And how does AutoSys work? AutoSys employs a hybrid architecture, decentralizing inference plane for system-specific interactions such as actuations and exploration, and centralizing training plane for hosting an array of machine learning deep learning algorithms with generalized abstractions. AutoSys employs a cross-layer solution, prioritizing jobs based on their expected gains towards solving the given optimization task and executing jobs. In AutoSys, a system decision making is formulated as a optimization task. And here's two cases of AutoSys and how AutoSys can work. The first diagram illustrates the first case where AutoSys predominantly learns from human experts. Handcraft the training dataset containing preferable knob setting for some system states and workloads. The second diagram illustrates where AutoSys predominantly learns from interactive explorations with the target system by automatically generating system benchmark can dedicate AutoSys collect measurements to train models. It's kind of like reinforcement learning. Here's overview of Webscale Search. The Webscale Search is a distributed and pipelined infrastructure. The first stage is selection service. Select relevant documents from web indexes for subsequent ranking services. It relies on both keyword-based and semantic-based matching strategies. So what logic does it uh, use? So the application logic is there are three logics: roles, heuristics, and machine learning based logics. First, we can see there's a KSE. Well, KSE is keyword-based engine. It matches keywords in user queries and web documents. Subplan knobs determine the trade-off between search relevance and latency. You can see there's a SSE. SSE stands for semantic-based engine. It selects web documents with keywords semantically similar to user query. In the middle, we can see ranking services. The ranking engine implements a ranking algorithm based on high performance lambda mart, which uses gradient boost decision trees. And we can see in all of them, there's a data storage. To store data, One common data structure of web indexes is the key value store. Web search employ both open source RockDB and customized solutions such as multi-level time and frequency key value store. Now that we get a picture of web scale search, let's move on to the complexity analysis. So the first kind of complexity is complexity. The source of system complexity has there are three kinds of system complexity. The first is heterogeneous class of decisions. In this category, there are application logic, system algorithms, and system configurations. Let's go through them one by one. First, application logic implements features that will fulfill users' requirements, so its decision-making process should adapt to user usage. The second, inference system algorithms. The infrastructure implements system algorithm to better support application requirements with available resources. Then comes to system configurations. The system configuration are knobs for operators to customize systems. For a multi-dimensional system evaluation metrics, optimizing multiple metrics can be non-trivial if they have different and potentially conflicting goals. Modern systems can also have meta-metrics that aggregate a set of metrics or measurements over time period. The last one is end-to-end and full stack optimization. Modern systems are constructed with subsystems and components to achieve separation of concerns. Since end-to-end system performance represents an aggregated contribution of all components, optimizing one component should consider how its output will impact on others. So there's all the system complexities. Now we move on to operation complexities. The first is environment density and system dynamics. Environment, environment density and system dynamics, hardware upgrade, and infrastructure change can offer new capability. They potentially alter the existing system behavior. Hardware upgrades might be rolled out in phases, so there might be multiple changes throughout the time. Modern systems have increasingly adopted tighter and more frequent software update cycles. These software updates range from architecture, implementation, to even data. Software behavior also can change with periodic patches. Then we have workload and diversity and dynamics. Interestingly, there can be non-trivial differences among the workloads that individual system components actually observe. Subsystems can target different execution triggers or depend on the output of others. Non-trivial system knobs, software logic parameters, hardware configurations, actions of execution script sequence, engine selections, and so on. Now we analysis all kinds the kinds of complexity that can be in the system. Uh, Now we take a look at how the AutoSys is constructed. First is design principles. So if you look at the diagram, to support scenario specific decision making, AutoSys implements a hybrid architecture. Specifically, a centralized training plane is shared across all target systems, and decentralized inference plane are deployed for each target system. To manage computation resources, AutoSys implements a cross-layer solution as optimization tasks and allow target system to prioritize jobs spawned by their tasks, allow computation resources to be flexibly shared. So to handle learning-induced system failures, AutoSys implements a rule-based engine to validate actuations. Let's take a look at our training plan. The training plan implements features to support both systems exploration jobs and machine learning deep learning training jobs. The first step is candidate generation, which generates knob values to benchmark for the purpose of building up the machine datasets. Then, then it will benchmark the configuration dataset candidates. So the final step is model training. A trial instance will get output are merged with the corresponding knob setting to form a tabular data set for training services to train model. Historical results are optionally stored in data store for model retraining or data sharing among similar scenarios. And let's take a look at inference plane. The inference plane implements features to support machine learning and deep learning, inferencing jobs, and optimization solver. Taking the current system states and workload characteristics as input, this job infer optimal actuations. These jobs are typically triggered by events, which are predefined by system operators to support service level agreement. Let's take a look at ad hoc and non-deterministic jobs. In contrast to traditional systems, learning-augmented systems introduce jobs that are difficult for system operators to provision beforehand. First, optimization tasks are ad hoc. They are triggered in response to adapting to system and workload dynamics, which might not exhibit a regular pattern. Second, optimization tasks have non-deterministic requirements. They spawn system exploration job and machine learning training jobs according to optimization process at runtime. To this end, AutoSys implements mechanism to prioritize, schedule, and execute these jobs. So now we have a somewhat a picture of how AutoSys is constructed. Let's move on. Okay, let's take a look at learning induced system failures. Um, so machine learning and deep learning being stochastic in nature, inference exhibits some degrees of uncertainty, and this uncertainty can lead to learning-induced system failure or suboptimality. To handle them requires different approaches. So first, uh, machine learning and deep learning models mathematically encodes knowledge and learn from training data. The meaning of their internal weight is not interpretable. Second, as model autonomously learn from training data, it is difficult to assess whether a dataset would guarantee a model to fully learn particular concepts. So here are um, some results of implemented deploy these algorithms to a real world. Um, we can see that is compared with expert tuning, the machine learning and deep learning can achieve same or better results on all aspects in weeks, if not days. Um, Here are some long-term lessons learned. Um, the first is higher than expected learning cost. There are unapparent trade-off of modeling an entire system deployment as one black box is the retrain cost. So any changes to deployment setup would invalidate the model. That would require a retrain. Retrain models for modern system can be really costly. Um, the second unapparent trade-off of the modeling is entire system deployment as one black box is exploration cost. Optimizing the job completion time for a cluster of hundreds or even thousands workers and jobs dispatchers. Preparing training datasets for this model scale can be challenging. So to mitigate this, um, to uh, mitigate the first one, there will be software modularity. Instead of modeling the entire system deployment with a monolithic model, we can modularize the training task into composable units of learning assignments. Software modularity is typically based on the criteria of code and functionality and maintainability rather than learning complexity. So even if we do modularize the system, it may not be optimized for machine learning. Let's move on. Um, and there's people of human in the loop. First, human experts can inject biases into training datasets. This is possible if human experts are already familiar with these regions. Model would exhibit an uneven distribution of uncertainties. To mitigate this, we can mix human labeled datasets with random explorations. The second is human experts can write conflicting specifications for optimizing tasks. Uh, Narrow down the search space by specifying the valid value range of each configuration knob. They can specify invalid configurations uh, if the invalid space completely covers the valid space. Any output would be rejected by AutoSys. In order to mitigate this, we can run a tool to check for overlapping conditions. Closed loop system control interfaces. First, some systems distribute configurable parameters and error message over a set of not well defined, not well documented configuration files and logs. Directly modifying configuration file means that the system can not enforce value checks or provide immediate feedbacks. Then parsing raw logs can be time consuming. Third, many system feedbacks are not natively learnable. To this end, customizing closed loops control interfaces for individual systems will mitigate that. Then we have applicability to other systems. AutoSys workers extremely well in well-controlled learning environments. Many target systems have a more relaxed learning environment. First, real-time exploration can be slow. especially for systems that requires a warm-up. For tuners based on bias and optimization or enforcement learning, training can take a long time. Second, online in situ exploration with production system can be restricting and even prohibitive. Our current practice is to construct base model offline by running explorations on testbeds or simulators, and then fine-tune models online with live traffic. Now we come to conclusion. Uh, with merging new technology like machine learning and deep learning, there are new ways to design a system. In paper pre- presented production measurements and discuss long-term lesson learned from operating system. Learning augmented systems should and will evolve over time. I would like to use a quote to end my presentation. Is by Alan Turing. It seems probable that once the machine thinking method has started, it would not take long to outstrip our feeble powers. They would be able to converse with each other to sharpen their wits. At some stage, therefore, we should have expect that machine to take control. That would be all my presentation. Thank you.